Hello, I'm MC Toon and it's Tuesday night. So excited for tonight. Tonight I have a flat earther that's going to teach me how to do celestial navigation. Amazing, amazing. Using flat earth, of course. Not using globe kind of figuring celestial navigation. So this is exciting. Brian Leake is the one who is going to be presenting. I will be the student and he will be the instructor. He's not here just yet, but I've got a couple things to show you before, while we are waiting for him. He told me that he'd be a little bit before he could be here. So no problem yet. No problem. I don't expect a problem. So last week on Friday, we had the Top Left Awards. And the big winner, as you probably already know, was Mitchell from Australia. Out of 31 worthy contenders, well, a couple weren't so worthy, but out of the worthy contenders, Mitchell rose to the top of the left and is on the top left of the Dunning-Kruger scale. Well done, Mitchell. Now, I asked him, I told him before, I sent him an email before the ceremony. Now, I knew he had already won. This was actually the only contact I sent out. I didn't contact anybody else, but I didn't want to break the news to him just yet. So I said, look, you're in the running for the award. Would you like to come on live? Look how complimentary I am to him there. And he gets a t-shirt. And I asked him so I could send it to him. He hasn't sent that yet. I'm sure he will be sending that. But yes, I did that. Then this was his response. He said he was not available, which I understand. People have schedule conflicts. But then this is his very next email to me. You can present it to me on Flat Earth Debate Show, 2 p.m. UK time on Monday on Nathan Oakley's channel. FTFE said he'd meet me there all last week, but is yet to show. I don't think Craig was aware of that, but that's a separate issue. Will you run and hide 2 or grow a pair? By the way, there's 3 Bitcoin up for grab for 1 globe proof. So he introduced the idea of this challenge, this in the very next email. Just to be clear, who introduced the idea of a challenge first? Of course, the 3 Bitcoin challenge is completely a fake challenge. I'll cover that a different time. So then, here is the a couple more emails went back and forth. I told him, hey, he won. Look at that. I said right here, congratulations, you won right there on the second. Your email shows how well deserved it is. Anyway, so. Like I always ask when people send me they say there's a 3 Bitcoin challenge. I say, well, where? Awesome. Could you send the link to the clear, objectively measurable acceptance criteria for that challenge? Nobody's ever done this yet. I don't know why. Also the details and how the money was put in escrow. And of course, the process for how the independent arbitration is done. I ask those 3 questions because I have a challenge. And all 3 of those things are in my challenge. The money's in escrow. There are clear acceptance criteria, measurable by any outsider. You don't need to have any subjective decision making in that. It's a true false, it's a binary, a Boolean decision. And then of course, should the sole judge, who is typically the one issuing it, should that person's opinion differ from the one that submitted the challenge, what is the process for independent arbitration? Because of course you'd want that. Because if the issuer of the challenge is the only arbiter, then of course it's a little unfair, a little biased, if you would. So anyway, I asked for that. He didn't provide that ever. Also, then I said, well, I do have a challenge myself, because that fake challenge, you'll never send the link. I have a challenge. Anyway, not really the point of the conversation there. And his answer, I just said, I said, good luck. Please indicate sextants cannot work on flat earth by deflecting or making unsubstantiated claims. Then he says, so I'll see you Monday, which is a deflection. tacitly admitting that sextants don't work on flat Earth. Anyway, it says, I'll see you at 2 p.m. on the Nathan Oakley channel then to present my award. Insert cowardly excuse for not being available here. I was there. I was there. And I was ready to present the award as requested. Now, it turns out that Mitchell had neglected to tell Nathan that he had invited us. So Nathan was a little unaware. That's fine. I can handle that. I'll still present the award. But Nathan wasn't. He was a little baffled at that I was there at Mitchell's request. Anyway, Nathan muted me. Muted right away because he wasn't interested in hearing that I was only there at Mitchell's request. So it's pretty funny. So anyway, I have a video covering this whole fun time that we were on there, waiting on YouTube, because even though I did bleep out Nathan's copious naughty words, YouTube still flagged it. So I'm waiting on a manual review, and once that's through, I will release the video. You will love it. It is fantastic. Later in that very show, somebody asked Mitchell, did you invite Toon and Craig on to present the award? And I have Mitchell's answer in that video. That's sitting there ready to go, just pending YouTube's approval. So there you go. That is super exciting. Let me read. I got a couple super chats from members here. Stringer News 1 says, Titicaca. Yes, Titicaca. I love it. And then William Foley says, Nathan was unaware. Ironic quote of the night. Yes, he's always unaware. Then maybe you saw earlier today, I issued I didn't issue yet. I pre-announced that there is a new challenge that I have, a new celestial navigation challenge. This one is, well, you can use any method you want to find the position. Now, this is a complementary challenge to the Flat Earth challenge, the $10,000 Flat Earth celestial navigation challenge, where they can only use Flat Earth presuming methods for it. And it's been like 5 weeks and not a single submission on that one. But the new one, the one that goes out tomorrow at 6 p.m. Central Time. I'm in Minnesota. People said, was it Central Daylight or Central Standard? I'm in Minnesota. It's whatever we have here. I think it's Central Daylight here. Don't quote me. I think so. So it's simple. I took measurements with the Theodolite app on my phone. Got screenshots. Put bars over the latitude, longitude, because that would be a kind of a giveaway. And all you need to do is, from these 3-star angle measurements, get the position within 25 miles. Pretty easy. And since it's completely possible, I'm quite certain that there will be many, many submissions. So I look forward to that. Even if you're wondering, should I do a submission? I don't know if I can get it in time to be the first one. Still do it. Oh, did I say that it's not hard. So I think I'm being generous by giving $100 to the first person. Somebody suggested I could have like 20 people and give $5 to each of them. Too late. I already issued it. So I can't edit these. That's the other thing. My challenges cannot be edited. I can't move the goalposts. Once it's done, it's done. And if I want to cancel a challenge, it takes 30 days to cancel it. I'm stuck. Unless it's not flat. Anyway, so that's the deal. It will be coming out tomorrow. It's just 3 screenshots. I'll have a video and the link on my website, which is already up with the full rules are already there. You can go read them right now. It's already there, ready to go for anybody that wants to read them. That page will have all the details you need. I've tested it myself already. And I got within about 6 kilometers of my actual location. So yes, and I'm mixing 25 statute miles with 6 kilometers just to mess with the OCD in my crowd, because I love you all so much. So, all right. I'm still waiting on Brian Leake. He hasn't showed up, and let's Let's see. I sent him a Zoom link, but no answer yet. So we'll see what we have here in the chat briefly as we're waiting for Brian Leake. So we got PGC. Let's see. Oh, you thought I was being cheeky and crashing his stream. Yeah, I wasn't. I was. Yeah. Yep. And I posted in Discord while Mitchell was lying about it. Oops, I gave it away. I posted screenshots of the email. So Brian looks like is connecting. That's good news. I hear him talking. I hear something talking. Are you there, Brian? I hear miscellaneous noises. Well, he's still connecting. We'll see if that goes. He's done it before, so I don't think he's gonna have too much trouble. Mr. X, Mr. Y. I do see that. And I agree. There we go. I see Brian. And now I don't see Brian. There, now I see Brian again. All right, hold on. He said, oh, he did this and then went away. So, all right. He's coming. He's gonna be here soon. I've got paper ready to go. I've got my flat earth map ready to go so he can tell me how to figure out the position. So Mr. X, Mr. Y, tell him to dump the phone and get a proper computer. Yeah, what percentage? What do you think? What percentage of flat earthers have a phone versus a computer that come on here? That's a good poll, shouldn't it? Shouldn't I do that as a poll? Let's see. What percentage of Flurfs only have a phone? There you go. And then it defaults to a yes/no question, which I'm not going to use. I'm going to actually put in. I'm going to pick the closest number, people. 20, 40, 60, 80. I won't do the bookends of 0 and 100. There you go, people. There you go. Ask him about the Artemis launch and the upcoming SpaceX missions to the ISS. That's a good question. But we are here for him to instruct me on how to do flat Earth celestial navigation. So I'm excited to learn this new information. I have to sneeze. Just a second. Maybe. There, you're glad you didn't hear that. My family complains, why do you sneeze so loud? Tough. Tough.
Can you hear me a little better, Mike?
Oh, yes, I hear you now.
Okay.
I don't see you. I don't know. Is that good or bad?
Look, I'm having trouble with my lighting and stuff, man. So if y'all want to take a picture or whatever of me, but this light's only gonna stay on for a second. But everybody knows what I look like. But let me charge this light and I'll turn it on in a little bit.
Okay.
Hey, I had a couple little special requests, man.
Okay.
One was that. Okay, I'm gonna just go ahead and disclose that I don't expect the money or nothing like that, but I expect to intrigue you. You know what I'm saying? I don't want to make this stressful or anything like that. You know, and spare me your comments. I'm just saying I don't want to make this about me. You know, saying no, that's bullshit. You owe me the money. You know, this, that, whatever. I just want to make this you know, intriguing to you and show you something where you might even be able to help with this. And just as, you know, you could humor yourself, but I had a special request though, for the sake of as far as giving you the location.
Yeah.
I will give you the location for the Flat Earth Challenge, and that should be at least worth $100 if you think, you know, that's, I'll leave that up to you, whatever.
If you get the correct location.
But let me say this: if I get the correct location, you said that for the Flat Earth $10,000 challenge, because I mean I am going to submit. You know, I'm going to submit my stuff that I have, and in hopes, that it'd be worth something. But I mean, I worked pretty hard on it and all that. But I want to say, I mean, would it be fair to ask you to go ahead and write down the second set of coordinates instead of waiting a couple weeks, just for the simple fact that where if you just take another random set of coordinates and maybe I could do it on the
Well,
spot, or maybe within a couple days. But my feelings is that I've almost got this formula zeroed in, but it might be, man, it might just barely come outside of that. It'd take you a while to find the angles to make it happen, but I think there might be one or two places, and if you had 2 weeks to do it, you could absolutely find the time to. I don't know. Is that one of the reasons you that you said that you wanted 2 weeks, is like to go over whatever's presented, or what was the reason you wanted to wait 2 weeks?
There's no 2 weeks in anything. Do you mean 2 days?
Or 2 days? I thought. Okay, my mistake. I thought it was 2 weeks to present the second set of coordinates.
Yeah, it's 2 days. So yeah, to review, the challenge is to, given the already published location, to send to me the solution. You publish it where you want, but then send me an email. But if we're talking now, that's okay. We've already emailed. And the exact methods necessary to do it, which of course this video could be. And if it doesn't use anything that presumes a globe or uses any numbers or formulas that are based on the globe, then you've successfully done the first set, the first part of it. And then within 48 hours, and I do the 48 hours just so that, I mean, I'm busy. If it's on a weekend or something or whatever, that I can have time to look at it if I'm doing some, out of town travel or something like that. Just some time, just some buffer. And then I'll send the second set of coordinates, and you use the exact same method to see if you get the same result, the correct results. Of course, if you send the details enough that an independent third party could process them, I'll know before I send you the second set of coordinates whether or not it'll work, because I will have already tried it. But anyway,
Roger.
But I can, if you just want a second set of coordinates, I can get you a second set of coordinates for you to try the same method on some other coordinates. No problem with that. I won't
just make it random, man. That's all I ask is when you send them, just make it random, and just for the sake of I don't think I'm going to have any competition with this, but just for the sake of the first set of coordinates, it would be 29 degrees 40 minutes 0.5
hold
north.
on. You caught me off guard. I didn't think you were actually going to have some numbers. That's great. Hold on. let me pull up to see. I have the numbers. If you can really, if you could do, people, if you could do what they do in CSI Miami, you could read it off of my glasses. All right, what do you have? Go ahead.
Okay, there's what I think you're looking for is let's see, 29 degrees 40.5 north, 36 57.0. That's got to be within a few miles.
That is certainly within the parameters.
Okay. And like some of these, I mean, I'm pretty much, just to be perfectly honest with you, I'm learning all this stuff within the last few days. I understood the concept and all that, but I mean, to get everything dead on, it's a lot of math, but it seems like the majority of it, like as far as the triangulation and everything, is involving a circle, whether you want to call it on a flat earth or a sphere. It's like a circle on the ground, or a two-dimensional circle, if you want to say that your sphere is a 2D surface. But so as far but you could also do it by trilaterization.
Trilateration.
Yeah, trilateration. Thank you.
Yeah.
So I think when Mitchell from Australia and Mr. Sensible were going back and forth, they kind of both had a point, because it seems like there's you could do it using both methods. Would you agree with that?
No. There is no triangulation in celestial navigation. It's trilateration. And so I don't know where you might use triangulation, because in normal celestial navigation, maybe with other there's dead reckoning techniques that might do it for you, but not with celestial navigation.
Yeah, well, you're laying out a circle. It's sideways, basically. It's sideways triangulation for your to figure your line of positions for your azimuth and your in the declination and all that. Like I said, it seems like there's multiple ways to do it, man. I'll look into that before I really get into a back and forth on that. But it seemed to me like it was triangulating positions according to the celestial equator, and
Where's the
that's
celestial equator?
it's basically, well, the celestial equator is basically the from the point of the vernal equinox, and it's basically like 23. It's basically like a invisible imaginary equator, 90 degrees of the North Pole. I mean, of Polaris, basically, of the GP of Polaris. So it's not completely lined up with the actual equator. It's basically the way a lot of people probably imagine the equator is before they imagine the Earth's tilt in the globe model, right? But it basically lines up the equinoxes and dips down to 23.4 degrees
Okay.
on one end, and then back up to 23.4 in between the equinoxes on the but you know what that brings.
That's the
Yeah,
Tropic of Cancer and Tropic of Capricorn, you mean?
right, the ecliptic, which some people don't like me calling that, but that's the solar ecliptic, right?
No.
Well, it's which where the sun resides in between Cancer and Capricorn.
Okay. Yeah, the GP of the sun is always between the tropics of Cancer and Capricorn.
Right. That's like I said, I don't want to make this whole thing about the sextant, man. So I brought a couple of other interesting topics, man, and I'm sure you have a answer to these challenges, but I'm gonna throw them out there anyway and see what you have to say, man.
Well, let's first can you go over how you got the position?
Yeah, pretty much. The first way I got it. Okay, yeah. Let me tell you my method here. Okay, now this is a method using this is a method. Method number one is basically trilateration. Is that what you called it?
Yeah.
Trilateration on the angles you gave by first converting the minutes into full degrees.
Yep. Decimal degrees,
then,
right? Yeah.
And basically using Google Earth as my map, with the argument that, and this is where the judgment comes in. You know, it's up to you because it's your challenge. But whether you think it's worth anything at all or not. But so I'm judging by a refraction equation based on the opposite side of my triangle being the GP of let's just say Polaris for explanation's sake, of 3959, being that's the closest we can get to no refraction, and that's traveling 69 miles away from the GP of Polaris, and triangulating 1 degree over 69 miles. So on a flat plane for the first degree. And so it's a refraction model based on, you could call it a celestial dome, or a celestial type of sphere, or you could call it a parent dome, but it's based on refraction. It's like I said, it's 90 degrees right directly underneath the stars when there's a minimum, if none, all to no refraction underneath. So that's where I triangulate, and I use that height to figure out the refracted amounts thereafter. So
all right. So let me see if I understand. You it sounds like you used regular global celestial navigation to get the answer, which makes sense because that definitely works. And there's online calculators you can use to just plug it in and get the actual number. And then you try to reverse fit onto Polaris specifically, and this what you're talking about here, Polaris, and then just arbitrarily applied the necessary refraction to give you 69 miles per degree.
yeah, kind of, man, but it's not necessarily arbitrary. It's a formula, and it's based on it's a ratio of it's over long distances. So I don't think this is anything anybody could prove or disprove within a day or just with but look, it's over long distances, and it has to do with the humidity gradient, and that's something I was going to ask for some help with at the end of this. I was going to ask for some help on that, but just for as far as the idea goes, it's based on a humidity gradient and long distances. So I'm going to need you to.
Oh, you cut out.
Just for the explanation of this, because it's basically, so it's empirical that we can go 69 miles and get a 1 degree drop in stars.
Yeah.
It's also agreeable that the further away from the GP of a star, basically, the more refraction. Now, obviously, my model is way more refraction, but it has to do with very long distances, and it's a ratio to that distance. So what it does is it's actually less math than the globe model, if you want to get technical, in my opinion. But I had to familiarize myself with all these equations.
This is just to get Polaris.
No. Okay, so you basically just triangulate. Okay, so you just triangulate 69 degrees. Okay, I mean 69 miles, 1 degree, basically 69.16 miles, 1 degree, and that's the baseline.
You could just say 60 nautical miles.
Yeah, we could say that, but anyway, I'm kind of in a habit, but it's either way you want to do it. But so now you have so we have established that the height of Polaris. So it's basically that's going to be the height to basically the stars above the flat plane. They got to be parallel with the ground for a couple of reasons. But let me go ahead and get to the point, and then I'll start.
Are you able to see my screen? Are you able to see my screen?
Yeah, barely. Yeah.
What do you mean? Oh, because you're on a phone?
Yeah, I see a dot. Yeah, okay, I see what you got. Yeah.
All right. So you start with this, and then on a globe, of course, all the math works out because the sun is far away and the light rays are very nearly parallel. But so you're saying though that for multiple observers.
Yeah, that's what I'm asking you. That's why I said I need you to entertain this for a minute while I give this explanation, because you're going to have more than one questions.
Yeah, it's entertaining.
Yeah, no, you like this. I think you will really, really like this, man. And I know the normal answer to this question is no, neither way. But some people would agree. Anybody honest and entertaining is if the Earth is a flat plane. And if it's not the ground curve, and it would have to be. I'm not trying to get you to say that, yeah, it's the light bending, but it would have to be. It would have to be some type of of light bending, just to work out the basic mass, right?
Presuming that the Earth is flat, it would have to be light bending. So let me draw a little bit of what maybe you're doing here.
Yep.
So close to, when you're close to this the GP, there's little or no bending, so that the angle is good, and then as you get farther, it bends more. So all right, so I got it almost. So all right, so this is what you're saying.
Yeah, that's what I'm saying. But I got a hell of an eloquent way to say it, though, man. So check it out. So yeah, that's pretty cool. That's pretty close. And
but it probably, though, the problem is.
Well, don't give me the problems yet before I've even introduced it to you. Before I even introduced it.
Okay.
And, like I said, you might have more than one problem, but like I said, I want to finish this at least. Okay. So now, if I'm just doing trilateration, okay, then I'm gonna do I'm gonna take your pretty much, get your calculator out for a second. Or I don't even know. You don't like to use a calculator. You got a machine head. You like to do it all by hand. But anyway.
Oh no.
So
I love to calculator shame other people. I mean, brag about my calculator.
Okay, good enough. So anyway, so you give me Regulus, which is 70 degrees, 48.7 minutes. Okay, so to convert that to degrees, I just divided. I just pretty much rounded up to see if I'd get close enough to even need to go into real specifics. But so basically, I just divide 48.7 by 60 and add that to the 70 degrees. So I get 70. What was it? Okay, then it's 70.8. Let's see. I got 70.8. Okay, 70.8 degrees. And so what I do is I take and this is where I say it. I'm not making up anything except pretty much the ratio itself.
Yeah,
so
except inventing the refraction ratio. Yeah.
What I'm gonna do is I'm gonna take 70.8 degrees, and I'm going to triangulate that with a opposite side of 3959. That's what I'm using. I'm using 3959 because that's what I calculated for the 1 degree with no little to no refraction. So go ahead and give me the baseline distance for 70.8 degrees with being the angle, the observer angle, and the opposite side being 3959. If you don't want to, I think I already have it.
Oh yeah, well, yeah, just a second. Yeah, you if you have it, you do it.
Yeah, let me do it, and if you could want to double check, it's so I if I'm okay, so I got 1,378.6. So 1,378.6 is my distance. So my equation is going to take 1 second because I just did one little thing. So it's basically, okay, so 90 minus A being the angle, over 90, over A divided by 90 minus A plus 90. Okay, and I'll write that out for you and I'll show you. Okay, times D, which is the triangulated distance we just triangulated, times point A, which is basically 1% of the angle. Okay, so here's what I got. So I got 90 minus 70.8 gives me 19.2. Okay, so that's the top line is 19.2, and then that's over 70.8 divided by 19.2. Okay, plus 90. So it winds up being I think 90. Let me see real quick. I should have had all this written down, but I don't. But I'm a little better prepared than I was last time I did this. So I'm gonna put it all together in 1 second. So I have 90. 90. Let's see, 70.8. Come on, 70.8 divided by 19.2. Okay, plus 90. Plus 90 is 93.68. So 93.68. So you got 19.2 divided by 93.68 gives me 0.204. Okay, so that's what I got. So now I'm going to take the 0.204, which is the ratio basically, or half of the ratio, and multiply it times that triangulated distance times 1% of A. So times D times point A is the way I put it. So I got 0.204. So I got 0.204 times 1378.6 times 0.192. Okay, so that's 53.9. So 53.9 is my refraction converted to distance from a ratio. So that's my refracted distance. So what I did is I took a ratio to convert the refracted amount into distance. And so I got 53.9. So my triangulated distance was 1378.6. So 1378.6,
Miles?
378.6. That was my triangulated distance. So distance minus the 53.9. Wait, minus 0.6 minus 53.9 equals 1,324 miles. Okay, so 69. So if we're going to figure that out for a globe, it's going to be 69 times, just roughly 69 times 19.2 it's off by 1/10 of a mile. It's 1,324.8, and I had 1,324.9. Okay, and that's the first one.
Okay.
And so the second one goes the same way. It goes Arcturus is you give me 27 degrees 9 minutes 0 seconds. So I'm going to do the same thing. I'm going to take the 9 minutes and I'm going to divide 9. I'm going to say 9 over 60. And that's going to give me, let me see if I wrote that down. That's going to basically give me 62. That's going to give me, let's see, what does that give me? Come on, what do you give me? Yeah, 62.85. So 62.85. So I'm going to do the same thing there. I'm going to say 90 minus A, which gives me 62.85. Because 27.15, 90 minus 27.15 is 62.85. Okay, over 27 or 62.85, or let's see, wait. Yeah, 62.85 divided by, nope, it's 27.15. Let me see which one it is. Yeah, 27.15 divided by 6.85. Okay, so plus 90. So I add that to 90 and then I equate. So I'm gonna say 27.15 divided by 62.85. Okay, plus 90. So I got 90.43 is 90.43. So I'm gonna have 62.85 divided by 90.43 gives me 0.6 Okay, so now I'm gonna multiply that times D times point A. So I'm gonna say 0.695 times the triangulated value for that was 7,719. 7,719.9 miles times 0.6285 gives me gives me 3372. Okay, so that's my refracted amount at that long distance is 3372. So I'm gonna subtract 3372 from 7719.9. What did I say? 3672. Okay, so 7719.9 minus 3372 point something. Okay, but besides that, okay, I got 4,347 miles. Okay, and that's within about 10 or 11 miles. Okay, that's the worst one that I've found so far.
Within 10 or 11 miles of what?
But let me go back and get this one exact. Let me do the next one, and then I'll.
I hope you can do it a little quicker.
Yeah, well, it's just an equation. I'm just trying to go through it in detail out loud. Okay, I'll try and do this one a little bit quicker, but I'm kind of doing it on the spot. Is I lost my damn sheet, to be honest. But okay, so anyway, the last angle is was Dubhe, and it was 55 degrees 18.4 minutes. So okay, I'm gonna put that in the degrees, and I'll get 55.3. So 90 minus 55.3 is 34.7. Okay, so 34.7. Okay, I'm gonna divide 55.3 by 34.7, and I get and that's plus 90. So I got 91.59. So 91.59 is let's see. So you got 91.59. So 34.7 divided by 0.59 is basically 3. Okay, it's 0.37. 0.37. Okay, so 0.37. My triangulated distance was 2741.3. So 0.3737 times 2741.3 times 0.347 gives me 351. Okay, 351. So I'm gonna subtract 351 from 2741.3 minus 351, and I get 2390.3, 2390.3, and for a globe the value is 2,394. So that's within about I guess 3.7 miles. And there are some of these angles are spot on, you know, and others, like I think the worst one was that second one. That's the worst one I found so far, but there might be a couple worse. But
So then a question then, just so that for clarity, when you get the distance from the observer to the GP of the star, right? Do you plot it on this? Or how do you plot it? How do you draw the circle of equal elevation?
If I plotted it on that, it wouldn't be.
It what?
If I mean, I haven't, to be honest, I haven't tried it on that because I'm basing this just, this is for the sake of my explanation.
Okay.
I'm basing my distances, you know, I'm basing them on a ratio of refraction that pretty much matches the flat plane to the globe. So to prove it right or wrong would take some extra. It would take some crazy,
some empirical measurements, I suppose, right?
It'd be crazy to try and go the distances you'd need, and I just don't know if we have the capability in reality of doing straight line for short distances.
Okay. Oh, you're cutting out. Yeah, you're are you in the garage? Come on. Are you loud in the house? I don't I got nothing. I got nothing from him. Well, so it sounds like he plotted it. He kind of force fit triangulation if I'm getting this correctly.
Latest distance we got from that first measured angle.
All right, hold on, Brian.
A.
You cut out for like a minute.
Oh shit. Well, I want to give the whole equation in nonstop, just real quick, so anybody can listen back if they're interested. So
Sure.
it's 90 minus a being the observed angle we measure, over 90 plus a over a minus 90, or 90 minus a. Sorry.
All right, hold on. You
Times d times point a. D
Right.
being the triangulated distance. That's it.
Start over. I'll write it down.
Okay, write this down. 90 minus a
Okay.
over
Got it.
a. Okay, over. Hold on one second.
Don't you have it written down?
Yeah. Well, man, where I had everything organized, I'm scrambling. That's why I was late, but I didn't find it. So okay, no. So over 90 minus a.
I got 90 minus a on top.
Yeah, and now on the bottom, you're gonna have 90 minus a over a.
Okay. And what is a?
A is the observed angle.
Okay. Okay.
So no, you're gonna have a over 90 minus a. I'm sorry. Let me make sure I get that right. You're gonna on the bottom, you're gonna have a over 90 minus a. Plus 9.
But
plus
hold
90.
on, hold on. I have this. That's wrong.
Put it closer.
90 minus a over a.
You can just write. Okay, for now, you just write that. But it's so where you have a at the bottom, where you have a. Hold on one second. Hold on.
Is it supposed to be the reciprocal?
Yes, basically, yeah.
Okay.
That's what you call that when you divide the
When you swap the top and
by,
the top. Yeah, that's called the reciprocal. Oh,
okay. What I need you to do is divide the observed angle from 90 minus a plus 90.
You want this one?
Yeah. No. First, I want first.
Hold on. I think Wiggles.
Hold on.
Wiggles might have it. Wiggles. Oh, dude. Oh no. He's just asking. This is difficult, man. I can't even follow you.
Not too bad, man. Not too bad.
Seriously, do you have it written down? Could you write it down and then read it to me after you write it down?
Sure. Okay. Let me do that. I'm gonna so 90.
That'll help.
90 minus a over a over 90 minus a plus 90. So I'm gonna word it like this so it's less confusing. 90 minus a.
Yep.
90 minus a over 90 plus a over 90 minus a. So, and then times d.
Hold on a second. I have a third option now. This is getting.
I was thinking you might be able to simplify this too, man. You know, that's why I was real looking forward to having this talk with you, because once you see what's going on here, and
so
and you might be able to. Yeah, go ahead.
All right, so I have 90 minus a over 90 plus a.
Over 90 plus a over 90 minus a. So you got to divide them on the top and the bottom.
Divide the top and bottom by 90 minus a.
So basically, let me just give you this as an example. As an example, your observed degrees for problem number 1, Regulus, was 70.
I
want to give you this so you can follow me in case you got a better way of wording this. So 70.8 is the observed. Okay, so that minus A, 90 minus that 70.8 is 19.2. Okay, so 70.8 being A divided by 19.2 plus 90. That's the bottom. So 70.8, that's A, over or divided by 19.2.
I need
That's 90 minus A.
I need some
plus 90.
stronger tune shine for this. This is
Yeah, I
not
was thinking
nearly
there might
strong
be a
enough.
way to do that with 180 or something and avoid doing that. But that's it basically. It's that times that gives you the ratio. And then times D times point A. So D is the triangulated distance times point A, and you take that what you solved there. You take this is what I did for all three of them, and I just subtracted that. Like I said, it's just basically a ratio. It's a ratio of refraction, which gets obviously more over distance, and you could call it. It's not really ad hoc because it's empirical, but I mean, it's only
empirical. It's only empirical if you see if there's like a measurement involved or something like that.
Well, I mean, what numbers are we using that are not measured? If you don't mind me asking.
Well, I mean, the measured radius of the globe would be one empirical number, but that doesn't really fly with flat Earth, because as Nathan Oakley says, you're going to need R for that. And
no, I'm not using R, but yeah, it comes out.
Where did 3959 come from?
That's empirical. That's me traveling 69 miles on my flat plane and observing a 1 degree drop in Polaris from the GP of Polaris. That's in fact that's where I'm pretty sure that's where they come up with the radius to begin with, because then they noticed that the further they went, and they probably had to check and double check because it gets harder to measure distances over, but they seen it was pretty consistent the more they traveled. So then that's when they come up with it's a sphere, because it's a whole lot easier. I mean, it's a lot easier to do the calculations based on the ground being a sphere. But like I said, if it's the ground is flat, then the light's got to be changing angles, changing degrees, because that's empirical. So I'm just basically taking a spot with the little or no refraction right up underneath. And that's what you get when you triangulate 1 degree. I think, in fact, I'm gonna go out on a limb. I'm gonna get provocative here and say that y'all hijacked my equation. They basically hijacked my my opposite side, 3959. So I got a beef with who is it? Who do I got a beef with? I got a beef with all of them, man. The sticks and shadows.
You got a beef with me. I measured it 4 times.
But you would agree that's what you get if you do triangulate 69 degrees. I mean, 69 miles, 1 degree. That's what you get for the opposite side, right?
Yeah, but on flat Earth, it only works for one measurement.
Yeah, before the light starts refracting, or like I said, I'm basing it on it'd be hard for me to prove this, man. That's why I'm asking you to entertain me on this, as far as making a type of model, because is based on a parent dome. Basically, it's not a real dome. It's an apparent dome.
The problem is, the refraction model that you're proposing, right? So you're proposing this, right?
Yeah.
Yes. I want to
solid. Yeah. That's pretty. Yeah. That looks about right.
Now the problem. So like here is like if you're right at 90 degrees north underneath the North Pole, and you can see the light comes down like nearly vertically, right?
Yeah.
Right. And then you get over here and it comes down at a different angle, right? And then you get over here and it comes down at another angle, and we keep bending it so that the light goes farther and farther before it hits the ground, right?
Yeah.
The problem is when you're at, say this is the equator, what angle does the light come into your eye for Polaris? Does it come from a high angle like this, or does it come from a low angle?
Well, that's where I had a challenge for you. but I'll try and answer that. Basically, it's coming in from everything's empirical the way we see it. So if we're at 1 degree latitude, we're seeing Polaris basically at 1 degree. But yeah, I mean, I don't think it's fair to start using observations right on the within 15 degrees of the horizon, because that's when they start breaking down on
I agree that the refraction does get more intense there. But all right, so the problem is, though, as you get farther away from the GP of Polaris, the light enters your eye at a shallower and shallower angle instead of a steeper and steeper angle like you just agreed to.
No, I'm saying the way you draw it pretty much for the math's sake's fine, but as far as I'm not challenging anything I'm not challenging anything we can measure. The only thing I'm challenging are the actual distances. I don't think we can measure them close enough, like say over 3,000 or 4,000 miles. I don't think we could get an accurate enough straight line distance to prove anything within 25 miles. I think there's methods, and some would work better than others, but it's all based on a map and or the stars and all that stuff. I mean, I agree it works like a charm, but I just don't think to prove it with like pulling chains on the ground would be extremely, almost next to impossible, man. But I'm agreeing with everything we see empirical. That's the bottom line, is what we see is what we get as far as angles. But like I said, it'd have to be the light changing. It'd have to be the light changing angle. If the ground's not curving, then it's got to be the light changing angle. Right?
Here's the problem with this one here. I asked you about this one and you agreed to it, but in reality, for it to work for you, this is the way that it has to go. Because you see the angle that the light comes in gets shallower and shallower with light bending this way. See that? You're muted. Or not talking or something. I hope I didn't break you. Okay.
Sorry, I was muted the whole time, but you're already helping, man. But I was gonna say to flip it, but I should have followed my instincts. But you're pretty much already helping. I'm not using this to say that this equation, this ratio, whatever, proves that the Earth is flat. But it's a model. I mean, if it is a flat Earth, then we agree it's the light. It's changing angles and not the ground. If the Earth is flat. And that explains the angles to Polaris challenge. I mean, as a flat earther, you got to imagine you get tired of hearing about angles to Polaris. So
certainly it would be tiring enough that I'd give it up immediately as soon as I examined it myself and said, "Oh crap, that doesn't work."
Well, I made it work, man. With
only sort of. Only sort of.
Yet either.
All right, so let's talk. Can we talk about this for a second?
Yeah.
All right. So, on the Earth, where is the, well, let's first do this. When it comes to refraction, here's the measured empirical behavior of refraction. When you have a higher index of refraction, light bends towards or away. Which way does the light bend when you have higher and lower refraction indexes? Which way does it go?
This is not terrestrial refraction. This is based over long distances.
Okay.
So basically the light over long distances, as far as perspective goes, even if the light is curving down at such a slow rate, when you're talking extreme distances, it's still going to fall behind perspective and appear to curve up, even if it is
fall behind perspective. Okay, well, let's
think about it.
We can do perspective later, and it sounds like you might be able to do a little bit of math, and we can examine that later. But I just want to look at, we're not doing perspective yet. We can apply that later. I just want to examine this and how refraction actually works, right? So when you have two areas of differing indexes of refraction and the light goes from one to the other, which way does the light bend?
Over long distances, it's going to appear to bend up.
That wasn't my question though, Brian.
Up.
It's not even a valid answer in
I thought you said what way does the light
Yes,
bend?
you have two areas that have different indexes of refraction, and the light transitions from one to the other. Right? Say it's coming in at an angle, right? So it's like from the Pink
You're trying to
Floyd
base it
Dark
on
Side.
Snell's. Are you basing it on like Snell's law and a change of medians or something?
Absolutely, Snell's law is what we deal with
Okay.
when it comes to refraction. Yes.
Yeah. Let me put my argument up forth. To so you can get on point with what you're challenging,
Okay.
or no, or at least know what I'm challenging here. Okay. So basically, as far as a change in medium between air being pressure, it's based on density. The air density is in my model, in my mind, even the little change in air density is insignificant. What it'll do to light, I think, in my opinion, it's the heating up of the humidity. And so let me finish. So
The heating up of the humidity. Okay.
yeah, of the humidity, basically. So humidity is an actual somewhat of a change in medium. So over long distances, I think that would take over. I actually brought some demonstrations, or I have some that I can post before I leave.
So yeah, when you
bending
just
upwards over long distances.
for reference, when you're calculating refraction, do you prefer the Cauchy equation or the modified Edlin equation?
No, I'm not. It's a whole different. It's not that. That's where I'm asking for some help. Is a way to make a coefficient for given that you take a look at this formula and all that. Like I'm just asking you to put your flat Earth hat on and coming up with the details on the humidity gradient. But here's what it's based on. Let me finish this real quick. So it's based on the fact that over long distances, the humidity gradient is consistent, because even if the humidity is down in a local area, it's going to gradiate to zero, at about the same pace everywhere or close to it. It's going to be a fairly consistent gradient that's going to change a little bit day and night. But basically, it's the humid air, the water vapor is less dense than the air without the water vapor.
Hey,
And
yeah,
so
that is a rare thing, Brian. Most flat earthers don't know that.
well, so based on so that's why I'm asking you to humor me, man, because I know you're familiar with all this shit, and I know you could take it to another level with some of this, and that's where I was going. So, in other words, if you're over long distances, especially like over the water, for example, over long distance, I'm not talking about up close within a mile or two, but over when you start getting past terrestrial refractive distances, the humidity, when it's cutting through all that humidity, it's going to want to bend toward the less humidity, and that's the only way that is up. And it gets colder as it goes higher, to a certain extent, and it also gets less humid as it gets higher. So I think it's a little bit of a transition.
Can I see if I can understand you? You are proposing that rather than the well understood behavior of the how humidity affects the index of refraction, that you think that it's drastically different than what's empirically measured, and that humidity is like the largest cause of change of index of refraction within the atmosphere.
Yeah, well, I would base that on two. I'll give two evidences. One is the
are they peer reviewed?
Yeah, one of them is, man. I got it from Gleam where he pulled it up. I can't pull it up right now, but just hear me out. You might be familiar with it.
I know where he pulls a lot of his stuff from.
You're right, but this has to do with targeting and how they did a study on how targeting people, like even launching like grenade launcher stuff like that, and short range to long range artillery, non-propelled artillery.
And they're using
they tend to come up short, man. No, they tend to come up short. It's just because of what they're seeing. So what they're seeing is they naturally come up short, and they've adjusted it. But also, it's based on I'll post this before it's over with. I have 5 examples of lasers, 10 plus miles each, with an orthogonal view of these lasers and seeing them bend upwards from a side view, watching them bend up. And also I have some short range that I got from Sky Free where they show because in my model, the basically the heat of the sun is basically is causing more refraction. You know, surveyors don't like to make their measurements early in the morning, and but to me the temperatures have had time to even out more. To me, when the sun comes up, especially over water, it's going to heat up the water, cause a lot of vapor. And I understand. Let me say this: I understand that your model, you know, the refraction and shit, the all that they've did the math to make it work. That's basically what I've did.
It's quite the opposite. You've done the math to make it work. I can show empirical measurements of the effects of humidity and temperature on refraction on my website, mctoon.net/refraction. I have a whole collection of papers of empirical measurements that people have done.
Yeah, but can you show me a laser beam bending downwards over distance? Can you show me something I can notice, you know, with real conditions, not laboratory conditions? I'm talking about with real life conditions. Can you show me?
You want a side view? You want a side view of a laser bending over 10 miles? You
know, just like 5+ miles, let's say. You got to be backed off of it in a way. I found 5 special examples where they caught the lasers from way off in the distance, off to the side, and showed. One of them's from right behind it though, and
so it's not from the side; it's right behind it.
Yeah, no. Well, the other 4 are. So let me fix my answer.
And did they measure the lapse rate so that they know for sure that it's not, you know, Snell's law?
They did in the short. I'm basically just going off the observation itself. So I don't have lapse rates for the lasers, but for the I do have the temperatures on the short range observations. I have the ground temperatures and the air temperature, as well as the water temperature and the air temperature over like over 600 meters in a lake where the curvature would have been the horizon should have been like twice that.
Wait, 600 meters?
Yeah, like 2 inches observation height.
So less than a kilometer, and they're doing it right next to the water where the refraction is the absolute highest and most unpredictable.
This is a different observation. This ain't the lasers. This was different. This was lasers. The one with the temperature readings. And they've done enough of them to at least compete or contest the fact that you could say it either way. I think empirically, I think you're going to have a hard time showing me. I mean, you might be able to. If anybody can, it's probably you. But you're going to have a hard time showing me like lasers curving down or short distances over flat lakes over short distance. Showing
over presumed flat lakes. That is what's in contention here.
It's flat because what I meant to say is before the horizon, so before the curvature of the globe model, so the flat section of a lake.
The presumed flat section of a lake. Okay. So no measurement. Anyway, well, that was a long way of saying that you basically have a different take on Snell's law, and you don't think it applies. Seems is what
over long distances, right? I'm not going to contest Snell's law, so especially like when it comes to glasses
but you are.
I'm talking about over long distances, man.
Yeah, but you are contesting Snell's law.
So Snell's law is used for say like 20-mile observations. They use Snell's law for that. You think it holds firm and solid, or do you think it averages out?
I think Snell's law applies. Yeah.
So if you've seen the North Maine surveyor, if you've seen his numbers for the Alberuni test, it's
the North Maine surveyor, yes. So yeah, his numbers when he measured
wildly inaccurate, man.
When he measured the dip to the horizon.
Yeah, he measured it all
Yeah.
these different days, and they're wildly inaccurate, man. And even after using the refraction, which was after using 7/6R, so 7/6R, you're telling me is based on Snell's law. So where did they get the
seven over
value?
7/6R is more appropriately used over land, not over water, and up above the land too, not directly. Not when I say above the land, I mean at some elevation, not near the ground. 4/3R is what the American Meteorological Society uses. That's more appropriate for over water, but not immediately over the surface of water, because when you're right over the surface of water, first few meters of it, the coefficient of refraction varies wildly. So
right, but it's still assuming a radius. You know, that's one of the main ways to measure the radius, but it has to assume the radius.
No, that's actually a pretty bad way to measure the radius. I would never rely on the zenith angles of the horizon as a good way with a tight margin of error. I want a tight margin of error when I measure the radius, so I'm going to do something different than that. That's not a very good idea.
Yeah. Well, look, man, I'll tell you what, though, I did work my tail off, man. Finding this freaking, I mean, it's harder than you think.
Here's
come up with something to line up with. All
right, so here's my question for you now. I got to give you this, Brian. You got the number, the location, correct to all decimal points. You got the exact number that I have in my document right here.
It's no coincidence, man.
Well, there's something. Let me tell you.
That's because I seen the video where you got them.
I
happened to, but I already had. Let me tell you what I had before that, though. MC Tune.
Very good. Very good.
Check this out. I got. This is what I had before that. And there's a few different ways to do it.
I can't see anything. So hold on a second. Let's explain here for people.
Let me tell you. Real quick. This is what I had before that. Is I had it was still within 25 miles, but it wasn't exactly. I thought you might get a kick out of that. But so it's so what I had was 20, it was 29.4 or 29 degrees 41.8 minutes. And then I had 36.568.
Okay. How'd you get those?
I did it a few different times, and I kept getting different numbers every time. But within the that's the one that I got was I'm trying to find my sheet, and it's pissed me off that I didn't get it. But the one that I got, and it was my 41 and 36 never changed. I mean my 40.
41 and 36. What?
My 40 never changed past like 41, early 41.
The minutes, yeah. So people know 29 degrees 40.5 minutes north, and 36 degrees 57.0 west. And I'll put that on screen for people to see here.
I meant to say this, man. I meant to say my degrees never changed. My minutes definitely did change, but the degrees, I always got them degrees. Even on the Mercator. On one of them apps.
You never used the Mercator?
But it would only let me do 2 at a time. And so I had to do Regulus and Arcturus. And then I had to do Arcturus and Regulus. I mean Dubhe. And then I had to do Regulus and Dubhe. And because it was, I obviously had 2 different spots to choose from until I did all 3 of them, man. But I was kind of rushing all this, man, and I've spent a lot of time out at sea, but that's using GPS and whatnot.
Yeah.
And GPS, saved my life one time pretty much. But even then, when it saved my life, I was looking at stars in between the clouds to just in case that thing. I didn't want to put my life in the hands of electronics, just in case that it failed. I was watching the stars track across the sky. And just checking the rate, it took me about 4 hours or so to get to shore. So
all right.
About every 30 minutes, I was tracking the stars. But
let's get back to the point here. So you got this exact number, these exact measurements from the video where I got these exact measurements.
Yep.
Okay. Which hey, good for you finding it. So that
I
is
didn't
that
mean
is
to.
no, that is where I got this particular measurement from, was from an actual video teaching celestial navigation. But now that particular, for reference, that particular ship had a bearing of 0 degrees and a speed of 12 knots, and it was a temperature of 12 C and a barometric pressure of 975 millibars. The eye height was 2 meters, and the index error on the sextant was 0.3 minutes. So to get this exact number tells me that either, as soon as you said it, I knew either you found the video or you applied all of the celestial navigation methods that they did in the video. So
I did take a picture of all the corrections and all that stuff, man. And
yeah,
but ultimately,
good
at the end of the day, just trilaterating was getting me close enough, man. I'll be honest with you. I just found that video this evening because I've been studying it. You know, I'm learning, and I just found that this evening. I'm like, oh my God, I've done all this work, pages and pages, and practicing and all
and
this
shit. Right there,
and downloading all this shit,
hidden
dude,
on
there it
YouTube.
was right there.
So anyway, that particular video, of course, uses the radius of the Earth. It uses the site reduction tables, which completely relies on the radius of the Earth. It does a positioning based on 60 nautical miles per degree. Everything in that video uses the globe. Everything. Now
It doesn't necessarily use the radius, though, man. It's as far as the
did it use site reduction tables?
Well, yeah, if you want to say that with the latitude and with the site reductions and getting your and working your latitudes, all that, but you could say that they're using my
so
equation
Brian,
pretty much, man.
What can you explain to the audience? What are the site reduction tables for?
Therefore, getting your pretty much, your line of positioning and getting your latitude, basically getting your azimuth and your freaking getting the GP of the stars, man.
No, the GP of the stars is not from the site reduction table.
They're for getting your azimuth, basically. Your azimuth and your what you call it, man. Your freaking your declination from the celestial equator, man.
Your declination from the celestial equator.
Yep.
So all right, the site reduction tables get you the ability to draw a line of position on your chart. Basically.
That's what I said first.
It's about the distance and about the angle to the GP. So you can draw it on your chart, draw a line there, and then you do it for all three, and you get your intersection. So the site reduction tables completely rely on the radius of the Earth. It's one of the factors that goes into the calculation tables.
If you're basing that off of the longitude and the latitude, but like I said, I'm not.
Which is what you do.
Okay, so where is the radius of the Earth one time in the
site reduction tables?
Yeah,
it's in the actual the math that generates the tables, and a fantastic demonstration of this was done by Flat Earth Math. I cannot recommend highly enough watching the video that he did, where he actually used Google Sheets. And he generated site reduction tables in Google Sheets and even mimicked the same format of the site reduction tables. And one of the numbers he input was the radius of the Earth, and another number he input was the 60 nautical miles. So you can't create the you can't create.
Or tell me who that was again.
Flat Earth Math. He's not actually a flat earther. He's a math teacher. So could somebody, Charles, could somebody get the link to that video and drop it in the chat here? I'll move it into the description too. So
here's my rebuttal to that. I can't really argue with that because it worked. Okay. But I would say this: the 69 miles per degree, however it's happening, is empirical. It's pretty much empirical to a certain extent. So. I don't, as far as height, when they ask about about the heights to the stars and all that stuff on a flat plane. That's why I come up with the equation because the heights are never a part of the equation, and
Yeah,
so it doesn't really matter the
exactly.
model. Yeah.
But if you're doing
But yeah,
if you're
so
doing triangulation, we you do a triangle on the surface of flat Earth, presuming flat Earth, you get then
Hello, everybody. This is
hold on.
an unusual.
Sorry, that was the video from Flat Earth Math that I clicked on and it started playing. So yeah, I don't know, 69 or 60 nautical miles per degree doesn't work because this is what you need to happen, which is the opposite of how refraction actually happens. So you have to presume that the Earth is flat, and you have to presume that Snell's law doesn't apply and something else applies, which is not empirical. You just post hoc invent it must work this way for your presumption to fit, which I understand.
Same thing with 7/6R. I mean, to me, every equation to a certain extent is made to match empirical measurements to a certain extent. But as far as it goes, you see what I did there, but the fact of the matter is that the trilateral was I had 2 points, man. But the trilateration is pretty much the part that you could argue the radius. But in my model, I could give examples though showing you light bending upwards. So it's not completely baseless. You could you got a good argument against it, and it doesn't go by Snell's law, but it does have an explanation in it. I do have empirical observations showing the light curving up over distance. So at least I came with something, man. Right?
You do have you may let's presume for a second that this does happen, but you explained it as immediately over water, where refraction is extremely volatile and high. But for this to work, you see, near the ground, and this is hundreds or thousands of miles high for the star on flat Earth. The atmosphere is down here in this thin layer. Once you get up 60, 70 miles, there's hardly any atmosphere left. And so you have the rest of this, where the majority of this bending of light has to happen in your model. There is essentially no air and essentially nothing, not even humidity, to cause it to bend. So there's no explanation. There's no plausible mechanism explaining why the light might do what you're saying it has to do.
Yeah, that's where the perspective thing comes in, man. That's where I was going to see. Like I said, I was going to show that to you, like separate.
Now we can calculate. Yeah, perspective is something that's easy to calculate. It is actually triangulation. You can draw a triangle, solve the triangle, and know the angle that the light or that the object must appear to be. And so we can do triangulation, but we can even do it without any math on this. Let me show you. You won't see. I'm going to show it to the audience. Then I'll show you afterwards. The angle that the light comes in. Let's use this one right here. This angle right here is, we'll call it theta. That angle now, if the light was coming straight, which it would. On flat Earth, except for the very bottom, it would bend the opposite direction. But let's leave that out for now because it's to your benefit. There's the angle right there. This angle here, we got theta prime, is this one here. Right there. If we just draw this to scale, right? So here it is. You can see it now. If we draw this to scale, Brian, and then we put a protractor on this angle, we can measure the angle. You don't need to do any trigonometry, and you can get the answer to the accuracy and precision of your instruments that you can do it to. If you want more, you can just draw it on a bigger piece of paper.
Comparing them to a globe, right?
No, this is just trigonometry. It has nothing to do with the globe.
Well, you got to have a baseline to measure it by.
Do you notice that this is for flat Earth? Do you notice right here? This is flat Earth. I'm doing this for flat Earth.
Yeah.
Okay. And I don't know why. Every time I do this and I draw a picture and there's a flat Earth on it, people are like, well, that's for the globe. No, it's not. This is for flat Earth. This is presuming that the Earth is flat. So you presume that the Earth is flat, and then you presume that light does this with no plausible mechanism for it. Then you say it's perspective. Perspective.
No. Wait, let me. I mean, you got other things to contest, but let me throw this out there real quick. What I meant by perspective. Okay, if you go over a severe long distance, okay, like let's just say 20 miles, just for example's sake, or the rate that the objects drop down, basically in our vision, the angle we'd get.
Yep.
For let's say something 1 mile high over 20 miles, if you drew that on a piece of paper and drew the line and drew your refraction ray diagram, if you drew it to scale, bending down to make the light appear higher. So if you showed the light coming up, the perspective would outrule the bend of that refraction. Because the ground drops off, at a faster rate than the light curves on your globe model.
I already had dinner. I don't need any more salad. So no. I mean,
what do you mean no?
Yes, no. So here.
If your light is refracting at 20%,
you talked about perspective. Then you added in refraction. Then you added in the ground rising up. You added. Let's just specifically talk about perspective of what would happen in isolation of everything else, and then you add things together. Once you make sure that you have an understanding of it, you add them together. So if this is your observer down here, and we've got this up here, and you said 1 mile. Let's say this is 1 mile high, and we've got a 20-mile distance, right? Now, if you move that 20 miles away, so now you're 40 miles away, it will drop. This angle right here will shrink, right? It'll shrink by a certain amount. Now, if you add another 20 miles, it'll shrink again, but it won't shrink as much. And you go another 20 miles out, it'll shrink again, but even less of a shrinkage. So every time you go the same distance away, the amount of reduction of that angle isn't as dramatic. That's because this relationship is an arctangent relationship or an asymptote relationship. It doesn't go down linearly, it goes down asymptotically. It never gets to zero, it just gets closer to zero. So it doesn't actually work for you because as you go as you increase the distance by the same amount, the angular change isn't the same amount. So on flat Earth, you would not get, due to perspective, you would not get the same drop. So you go 60 nautical miles, you get a drop in a degree. You go 60 more nautical miles, you would not get, on flat Earth, you would not get an additional 1 degree. You'd get less than 1 degree drop. Then you
you get more. You get more. In my model, you get more
I'm specifically talking about perspective. In isolation.
Yeah, I was talking about globe. I was talking about globe perspective.
No, you're not trying to prove the globe, are you?
7/6.
You're arguing for flat Earth, Brian, not for the globe. Let me remind you there, okay? You're arguing for flat Earth, so you need to show how it works for flat Earth.
Am I?
You're not doing a great job of it. I think you're convincing people the other direction for the most part.
I'm asking you to follow me. Just follow me. You follow me thus far. The value, the K value, okay, the rate of light bending over a distance on a globe,
the coefficient of refraction,
is less.
Okay.
Is less than the perspective drop over once you get to like 20 miles and beyond. It's so even if you show the light curving up, the stuff dropping in the distance that you're seeing is outpacing the the rays in the first place, just from them getting lower due to distance. So even if the light is bending down, once you hit a certain distance, even them are going to have to perspectively come to your eyes upwards, basically, to even if they are bending down. What I'm trying to say is that over long distances, the ground's going to drop off at a faster rate than the light is curving.
Brian, I appreciate that you try. I do.
Do you agree with what I'm saying?
No.
When you hit a certain distance, the curvature is exponential.
No, it's not.
So it's going to surpass that of the refraction, right?
On flat Earth, it's logarithmic. Not even it's
on a globe.
Asymptotic. You are arguing. Stop trying to argue for the globe. I'll handle that part. Brian, can I read a few things here?
Yeah, go ahead, man. I'm on.
Some audience feedback here. We've got Stellarium Celestia says, "Boop that like button." Thank you for that. Elia Baca. Isla Baca. Oh, jeez. Says, Brian, the words you forgot are spherical geometry. I had this out earlier. I don't know if you saw it, but Eddie Reese asked, what's my quickest time for solving a Rubik's Cube? 1 minute. I did it once under 1 minute. I don't try to do it fast. Mark Beiser. I like Mark Beiser. He drove me around in Texas. He says, rainbow mathaderp and then a chocolate snow cone.
Well, if you graph it, you get a parabola, basically matching Earth curve for as far as I did it, But I wasn't trying to say Earth curve, but what I was trying to say
hyperbolic.
I was talking about perspective, like on a globe model. I'm not trying to prove.
I don't know why you're talking about that. Your challenge is this. This is your challenge.
Refraction has a certain amount, depending on the air temperatures. What I was saying is over long distances. But anyway, I don't got to keep saying that. My point is that I just wanted to mathematically come up with something that if I was out to sea, pretty much I can trilaterate. When you're using a sextant, the triangulation is based on the celestial equator. Basically, it's based on the sphere, the celestial sphere is what they call it. Basically, parallel with the curved ground, basically. So it maps out the same as a flat ground and a flat celestial, whatever you want to call it, plane. But except for the linear, over distance, it getting bigger, So that's why I just come up with an equation that would apply and get me to shore if I wanted to trilaterate. And I've worked pretty hard on it, man. It's I fine-tuned it a couple times. So yeah, you could say it's ad hoc, but like I said, it's still an equation based on empiricism. Like, to me, 7/6R is arbitrary, because where'd you get 7/6R?
That was measured.
That'd be my argument.
Gauss. That's where came from. Gauss got it. He measured it.
So who measured 4/3R?
I don't know the history of 4/3R, but the American Meteorological Society seems to like it. I didn't look up where that is, but well, yeah, it's so the ratio of the radius to the radius of the Earth to the radius of the light, the arc of the light as it passes over the surface of the Earth. Because we know that the Earth is a globe, there's no question about that. It's convenient to use that as a ratio between the radius of the Earth and the quantity of refraction, because it makes the calculations easier. Now, but here's the thing: 7/6R, 4/3R, those are just estimates that are used if you don't know the actual lapse rate. and it's known that it's not fantastic, but it's better than not having anything because it gets you closer. It reduces your margin of error. That's all. So, all right, let me read a couple more things, because Stringer News 1 says, when your grandma insists on driving and takes 2 hours to get out of the parking space. I think he was appreciating your formulas there. Brian Preck says, Rumpus. Brian Peck says, Rumpus takes less time to make a diagram than this.
Well, okay. Man, I'll be honest. I left my my freaking equations where I had it mapped out, and I had all my stuff. Man, I couldn't find it. And I was late. I was looking for that stuff.
Did Rumpus come by and steal it? That's just like, anyway. So people know Rumpus can take a long time to explain things. William Foley says, I think my brain is leaking out my ears. Oh, you see what he did there, Brian? Because his last name.
Yeah, that sure was original.
Yeah, I'm sure you've never heard that. All right, Earth is Life. You know that. You know him. Earth is Life says, Brian, learn about linear relationships. Or what's not a linear relationship, like perspective.
Yeah, exactly. That's my whole point. Perspective is not linear, and neither is Earth curve.
Yep.
Not from a point.
Yeah.
You know what I'm saying?
Exactly. And neither is it parabolic. Chronic Avenger says, you have a drastic refraction in varying conditions. Why doesn't it change?
Like I said, it's based on a humidity gradient that's pretty consistent everywhere, and it's over long distances, man. So you're not going to get very much deviation from it, even if it's dry. Like in a spot one day, if it's drier than usual, the gradient is not going to change much, and you're talking over long distances.
But Brian, it's in the air. We know it's temperature that's the major influencer, followed by pressure. Humidity is significantly farther down.
It's colder the higher we get, right?
Yeah, and the pressure goes down too. So in the lower atmosphere,
I could argue that because if you're looking underwater, looking at an Olympic pool or underwater, you'd think if it was the pressure of the same medium, but just the pressure, the water, so the atmosphere the gases don't change much on the ground where we observe. You don't see any refraction in a clear swimming pool or the ISS test chamber, per se. You're not going to see any refraction up or down, even though the pressure is going to gain a lot.
You
more
mean
rapid in a pool of water than in the air? Between
the top of the water and the bottom of the water, or between the air outside the water and the water?
No, the water, the top of the water and the bottom.
Okay.
And I'm not talking about looking out of the water.
And how did you measure that?
I just looked at it. I was curious because I was like, man, can the pressure? I was looking for real life examples of stuff.
Yeah.
Man.
So wouldn't it make sense to maybe get a predictive formula that's based on empirical measurements for the difference in the coefficient of, or the index of refraction within water based on pressure? That'd be a good idea.
Yeah, you're not going to get.
I just looked at it and I didn't see it. That's not very solid there.
Yeah, you're not going to see it. That's my whole point. So if you're not going to get refraction underwater based on the pressure difference, why in the world would you get in air where there's less of a pressure difference?
Because they're different mediums and they behave differently. Oh dear.
Right, but air is the same medium at 10 feet as it is at a mile. It's just basically less pressure up there, right?
Less pressure, yes, absolutely. And pressure has a major contributor to the index of refraction.
My point is, underwater, I looked to see if there was refraction over long distances in clear water, and there wasn't.
How did you do that, though? You just in a pool. A pool isn't a long distance.
Dude, calm down, man. Chill out a little bit. So in the pool, and or other bodies of water that are clear, the pressure differential is way more than in air. But since it's the same water at the bottom of the pool as it is the top of the pool, pretty much like looking from the shallow end or deep into the shallow end over like 100 meters, you would expect to see more refraction because it's going to be hotter toward the top.
How much more?
Some at all.
Give me a quantity. Quantify that, please.
Just some. No, I haven't worked on the quantities yet, man. That's why.
All right. Well, work on that before you start making claims. Maybe. How about that? That's a good idea.
I'm basing on the empirical what we can see, and And what I'm basing it on, I got to base it on something. So I'm basing it on shit we can find.
It's just a hunch. So that's a good hypothesis. Work on that. All right. So let me keep going here. Omega Red says salute to the greatest rapper of all time, and then he says MC Tune, which doesn't follow. He says, oh, maybe he's talking about himself. I don't know. He says, and I'm a black man from South Carolina. Well, Omega Red, I could not ever take the greatest rapper of all time. I am definitely no good. Cretan Bull says 25 months and still no evidence for flat Earth. Yeah. This Stephen K. William Foley says love how he gish gallops himself. Focus, Brian. Focus. Brian's he's trying. I like it. I like Brian. Cretan Bull for 2 Australians says 28 months. Wow. Time flies, huh? Time flies. He's been a member for 28 months. Very nice. JSS Tiger for $5 says, why do flat earthers turn perspective into convoluted science? Brian, perspective is actually pretty easy to do.
Yeah, I'm aware of that, man. I mean, I went back and forth with Ruhif on, and I figured out, I had to brush up on a lot of things, that I left behind in high school and shit on some of the math. But as far as the perspective, that's one of the first things I brushed up on was the angular heights and shit to shit like the Blackpool Swan and all that. And the only point I was making about that is that, like I said, the curve gets exponential with distance. So if you're looking from one point, it's gonna. Only point I was making. Let me try and word this a little bit different. It gets
asymptotic with distance.
Yeah, the drop of something in the distance is gonna. Yeah, the drop of something in the distance starts accelerating. So at a point, it's going to overtake the given refraction of light. Was my whole point. I wasn't trying to use it as a proof. I was just trying to give insight and somebody something to kind of picture in their head,
Okay. NA for $6.66 is wondering, is that his cube? Yes. I'm keeping it warm. Dang it. I feel guilty. I gotta do it. I gotta send it. Brian, will you help me send all of the things that I owe people?
Yeah, I wish, man.
All right.
Dude, I just went negative, man. My account. I got
all
paid,
you need to do is remind me. Brian, to send me a message tomorrow saying, hey, did you send that stuff yet? How about that?
Yeah, all right.
All right. Master Khalik says, Brian admitted that the globe model is the best model we have. Why are you still denying it?
As far as longitude, latitude, because think about it, man. Think about it. If you're gonna this is the point I wanted to get to, man. And since we're getting stale at this point, I wanted to start talking about the globe model and the parallel rays and whatnot. I've seen a proof on a channel that the first one I seen was where you could see the sun rise multiple times, but then just by laying down on the beach and then standing up. But then I seen a video, I forgot who it's from, but I seen it through Rich Mr. Thrive and Survive's channel, where they were arguing at one of the buildings, like it was up like on the 20th floor or whatnot, that they would have light coming in upwards or whatever, or they could go up and see the sun set again or rise again, depending. And according to the globe model, the horizon is 0 degrees, basically, or real close to it with a little bit of adjustment. Surveyors use it as 0 degrees. So if the light is coming in parallel, you'd have to go up 3,660 feet to get a 1 degree change. So if you only went up 20 stories, if the light is parallel coming from the sun, that's on the horizon, if the sun's sitting on the horizon and the light is shining like on the bottom of clouds or whatnot, or like the shadow on the bottom of clouds with the sun sitting on the horizon, you got a problem to me, if you stop and think about it, you got a problem, because if the sun is sitting on the horizon at, we'll call it 1 degree, then I would have to go up. I'm not talking about the ground changing either. So if you'd have to go up, basically, if you went up all the way to the moon, even, you'd still have the same angle to the sun, just about. You'd have to go a little over 1 million miles to change angle. Now, I agree that if you go higher, the horizon would drop down. Okay, but what I'm talking about is down at ground level. If the sun is 1 degree, you got to go up 3,600 feet for the ground to drop 1 degree. So that's kind of one of my first points on parallel sun rays having a problem. And that picture with the shadow shining on the bottom of the mountain with the sun sitting on the horizon, they're back away from the mountain. They're back away from the mountain, probably 20 miles or so. I mean, for the mountain to look that small, they're probably more like 50 or 100 miles, but we'll just say 50 miles to average it. So, and the sun's on the horizon. So for it to shine light upward from that distance, that's going to break the parallel sun rays theory, or whatever you want to call it. If the light's parallel, if it's the sun's sitting on the horizon, if I went forward closer to the sun, the 50 miles, that would be, it would be even, I mean, you see what I'm saying? As far as the sunlight to change 1 degree, you got to go over 1 million miles. You'd have to go up higher than the sun.
That's not what's happening. But
what's happening then?
Let me draw this first. I'm working on something here for you. A little drawing for you.
And while you do that, I'll think of a better way to word this, man. I admittingly ain't wording this argument very.
So, all right. So I've got here. I'll fill it in here with a little bit of. There we go. So I've got sun. I've got clouds. I got a mountain. Right? You see that? So, and now notice that I drew the ground flat. This is presuming flat Earth. All right.
Yep.
So now explain to me, please, how the sunlight from that sun there can hit the mountain and then cast a shadow upward on the clouds, please.
That's all right. You just reminded me of the way to word this. Okay, so if I'm 50 miles away from the mountain, the mountain's in between me and the sun. So if I work my way to the mountain, okay, then it's going to come up almost another degree. So if it's sitting 1 degree on the horizon as is from me 50 miles beyond the mountain away from the sun, then it's going to be about 1 3/4 degrees by the time I get to the mountain.
It doesn't, so Brian, it doesn't matter where you are. I'm not asking about your view. I'm asking how does the sun shine? How does the sun shine on the bottom of the clouds and cast a shadow?
Exactly. If you have a sun that's 1 degree above the horizon, and I made a video showing all kinds of images with the sun sitting on the horizon and a little bit above the horizon. Okay, 1 degree, even up to about 3 or 4 degrees, shining light on the bottom of clouds. When, like I said, to get if the sun's rays are coming in parallel, to get a
Brian,
1 degree upward,
this is flat Earth. This is flat Earth, Brian. Don't change topics. I'm asking you how this happens on flat Earth.
The light bending upwards. Remember my model.
Yeah, but what's a plausible mechanism? It's just an ad hoc, wishful thinking.
Well, like I said, all I could do is give you the ratio of how I have it working on my model and show you it light bending upwards in real life, and that's all I can do.
All right, so you don't have an explanation. You just have a plausible mechanism. You just have wishful thinking. Humidity doesn't solve it for you either.
Humidity gradient
doesn't solve it for you either.
Well, would you at least say that it's arguable that a humid environment gradiating to a zero humidity environment could play more of a role in long distance than just the same medium with just a little bit of pressure difference?
No,
Well,
because humidity is such a small impact on it compared to pressure. Pressure is drastically larger impact.
well, can you show me in real life light bending downwards without using your model and saying, look, these match the model? Can you show me
Surely
a laser?
you've seen.
Can you show me a laser beam bending downward
Yeah,
in
surely
real life?
you've seen Mick West's doing that.
With a laser?
Yeah,
No, I haven't. I'd like to see it.
you've not seen Mick West. Oh
You
dear.
talking about in the fish tank?
Yeah.
No, I'm talking about in real. I'm talking about in
Yeah, I don't.
the-
I don't care about your denialism. It happens in the lab. It happens when tested. It happens empirically. It happens in an experiment.
settle down, MC Tune. MC Tune, this is a debate, man. Don't get all worked up on me. You're doing too good. We're doing too good, man.
So, all right, I can show you it empirically happening where the coefficient of the index of refraction is varying and having a higher index down low and a lower index up high.
I understand that, man. But like I said,
Good.
you got
All right.
that on me. You have that on me, and what I have on you, the only thing I have is demonstrations of light bending upwards over the medium we see through. So I'm going to throw that out there as evidence to toward my model. So it ain't like I just came with just numbers. I'm gonna have to refer you to a video on my channel that's called Celestial Refraction Model. A few months ago, and the first 10 minutes shows up close examples of upward light refraction with temperature measurements and distances and comparisons and long distance lasers. Like I said, with side-on view, orthogonal views, showing the light bending upwards in the environment atmosphere that we see through. So at least I brought something, man, not just nothing at all, right?
So yeah, so in a limited sense where the index of refraction is unknown, it might be happening. Okay. Let's see.
That's the best I could do, being honest, keeping it real, man. But it's just a model, and like I said, man, hopefully I've piqued your interest enough where you could help me with working out a coefficient to over long distances. If I give you some of the data, some of them, if you could just help me for my sake,
I don't know if I'm going to be super excited about doing your work for you, Brian.
Just help me. You don't got to do it for me. I'm just saying, if you could point me in the right direction, maybe.
All right. Well, send me if you can be communicative in Discord, that would be good.
Okay.
Let's see here. I've got a couple more questions, but let's see. Trying to set this up. I have another one. I'm scheduled. Where is it? Set up. Nope. Anyway, won't do that. Couple more questions. Let's see. Stephen K says, quote, "I left my homework at home," unquote. "Didn't work in school. I don't know why you would think it works here."
No, I just had it all written down in order, and I had a lot of my notes.
Do you have a dog?
I redid pretty much the three and everything, but I had more.
Do you have a dog?
Down where I could just recite it word for word. But no, I don't have a dog. I have cats, chickens.
Did the cat eat it?
Nope. I think it got thrown away, man. I'll probably find it right after the debate. But it doesn't matter.
The cat got thrown away? Dude.
No, I said it probably got thrown away. But I said that
the cat.
It doesn't matter at this point. I've already pretty much rewrote it and to recite it. It would have been a little quicker if I would have just been able to recite it word for word like I had it written. So that aggravated the shit out of me, man. Trying to find it, it was even more aggravating. Probably got thrown away. But I just redid it and did the three angles that were given in the challenge, just to show you.
Send me your formula, because I could not and nobody in the chat, if people were guessing at your formula, I have a stack of, oh my gosh, I have a stack of papers here. I don't know. lost in the pile. All right. Sean Hawkins for $5 says, why does Brian refuse to be humble whilst demanding humility from others?
I don't have many words for that, man. Not honest, man, in my opinion.
Q Lexia says, if I had a cat, I'd use a catapult because that's what they're for. I built a trebuchet, big one.
I'd like to catapult these cats, man. And I'm about to have a batch of kittens, and it's only going to get worse from there, man. I got stuck with my youngest daughter's cats, man, and now they're multiplying on me.
I love cats, but I just can't eat a whole one. All right, are you coming on screen? Hold on, wait, what are you doing here? You got to warn me so that I can.
No, I'm not coming on screen. I was pacing around. I hit the wrong button, but
all right.
Dude, if shit ever hit the fan, McToon, and that'd be the only way I'd eat a cat, man. I don't know if I could eat my own cat, man. Kind of crazy, but if shit ever did hit the fan and people were hungry enough, I guarantee you that pets would probably be the first thing to go if it came between life and death, huh?
I suppose it would be a thing. So here's what I have coming up. Oh, George Natchik says, I have seen Brian's formula, and it's BS. A key parameter is not derived from first principles. Yeah,
you ain't seen my new formula because I just introduced it tonight.
Ooh. There you go. Well, send it to me. George will be interested to hear of it as well. But yeah, it does sound like you plugged in the radius of the Earth and you plugged in the distance between nautical miles, the 60 nautical miles as 69 statute miles. So,
let me say one thing real quick. If anybody goes and looks at it's a couple months old, the celestial refraction model. The equation I show at the end, it's similar to that, but it is modified. And it's a ratio. I'm working on evidence. I'm working on two things. I'm working on getting a coefficient to show something over long distance. I have the examples to show empirically the light bending upward, but I don't have the math for that. And also when you get real close to the horizon, even though it kind of breaks down a little bit on the globe model too, I still, this is where I think terrestrial refraction on a flat Earth would have to join in at 1 or 2 degrees, or a few degrees to the horizon. So I'm working on a model on the math for the terrestrial refraction, where low to the ground it is involved with the celestial refraction to make it more accurate all the way to the ground.
Okay. I'm anxious to see it. Anyway, so for Brian, you can join in and watch the next one. The next stream I have is going to be, I called it an invasion. It's not an invasion really, but we're going to find somebody that's on YouTube doing a live stream, but doesn't have like hardly any viewers, and we're all going to go there, and we're going to be nice to them, and then invite them on to talk for a minute, on here live. So last time we did it was
say that again, man. You're gonna go where?
We're going to find somebody on YouTube somewhere that's doing a live stream, but has like a very small number of viewers. And then all of us are going to go watch that, going to join in that live stream. So the numbers will go from 5 to 20, 50, whatever number of people are there. And that person will be like, whoa, that's cool. And then we'll say, hey, come on, let's do it. Let's come on to my show right now. And we'll just do an interview right here, right now. I did it a while ago. It was pretty fun.
Are you referring to like flat Earth channels?
No, probably not.
Okay, but so in other words, if the topic's interesting enough, then you'll watch it and invite people and
probably
and
won't
invite
be
them.
a flat. Maybe it'll be somebody doing a tarot card reading or a palm reading or gaming or talking about spinning dryer lint into yarn. I
wanted to bring up one other point, man, before I gotta go.
Okay.
Shortly. One other point is that would you agree that that a 90-degree turn from the North Pole from the GP of Polaris. Any 90-degree turn on the globe model is a great circle.
Any 90-degree turn.
Yeah.
So if you start at you mean like if you start at 90 degrees north.
Yeah, if you start directly underneath Polaris.
Yeah, and then go well.
If you go down any given longitude.
Yeah. That's a great circle. Yeah. Yes.
Yeah, and you take a right turn, it'll be a great circle. Okay. And
I don't know why you need a right turn. You mean you have a 90-degree angle between the line from the surface of the Earth.
You'll have two perpendicular.
Yeah. Okay.
Any 90-degree turn from the south or the North Pole off of any
or
horizontal
from any GP. But yeah. Okay.
Yeah, exactly. And then because the latitude in the globe model, all the longitudes are great circles, but the latitudes, the equator is the only great circle.
True.
Okay, so I asked you, having agreed to that, would you also agree that if I'm on one side of the Earth, let's say 1 degree from the equator, north, 1 degree north, and antipode around the equator, just follow it on around, follow the great circle, whatever, on around, and somebody on the other side is on the equator, or let's say they're 2 degrees north of the equator, and we're antipode on the globe.
Antipode from the if you're near the North Pole, the antipode is going to be near the South Pole.
Besides a degree.
Yeah, antipode's going to be near the South Pole.
No, well, not antipode then, but opposite. Let's say that, opposite the circle, and then go up 1 degree. This ain't the challenge yet. I'm just making sure I put you on the same page.
All right.
Visualize this. So we pick a spot on the equator.
So you are at 89 degrees north.
270. Let's say 90 and 270.
There's no 270.
90 and negative 90.
It's 90 south.
Okay, let's do this. Okay.
90 north and 90 south?
No. On the equator. On the equator. You say there's no, I'm just saying 270 to make it simple.
No, saying 270 doesn't make it simple.
Okay, if the prime meridian is 0, let's just say the prime meridian 0, okay?
Let's just say that, yep, that's what we use. Let's just use what we actually use.
All right, and we go 90. I understand that it repeats and shit, and you don't go past 180. I understand that.
Okay.
But I'm just saying, for people to visualize this at home, let's say somebody's at the prime meridian, and then somebody is 180 degrees. Let's word it like that. Somebody's 180 degrees around the globe on the opposite side of the Earth at the equator. Okay, you with me so far? Okay, now one person goes forward, goes north 1 degree.
Okay.
And the other person goes north 2 degrees.
Okay.
Toward Polaris. Okay. Now, so you'd agree that if they kept on going, they would circle back around and until they came back at their position. They do a longitudinal great circle pretty much.
Okay.
Okay, so they go 1 degree and the other one goes 2 degrees. Now we go to observe Polaris. Okay. And in the globe model, Polaris has parallel rays for a whole long way. So the person at 1 degree is going to see 1 degree above the equator is going to see Polaris 1 degree above the horizon, and the person 2 degrees north of the equator, opposite, is going to see Polaris 2 degrees above the horizon. So if you take them 2 people, it's not the angle of the starlight that's curving, it's the ground. So they got a parallel shot to Polaris. They would never intersect. So if they were, let's say if they were almost, 7,900 and what you call it miles, the diameter of the Earth, if they had laser beams coming out their eyes, they would start on their great circle toward Polaris. Okay. And they wouldn't intersect. They would hit their laser beams would hit Polaris, and they would be the same distance apart as they were on Earth because of Polaris's perpendicular rays. You agree with that?
There's a lot of words that were said there. I don't know if I can agree with it. I don't know if it makes enough sense to agree with.
You don't agree. Well, if they're two great circles, if they're two longitudes, and they're not, they're a couple degrees off, so they're not they're not basically converging.
Oh dear.
Because they're going
Brian,
straight off.
Brian, maybe
they're going straight off to Polaris, right? You're leaving the Earth behind, and you're going straight off to Polaris. The fact that we are not the same angle makes the light from Polaris, makes it perpendicular. It's the ground that's curving, not the light rays from Polaris. That's the whole point.
Yeah. Thus the Earth's a globe. I'm loving where you're going with this, Brian.
The point would be if you take and you go and you start at the North Pole and somebody starts at the South Pole, and we take a 90-degree turn, like about where I'm at, close to 30 degrees north, and you take a 90-degree turn, and then somebody from the South Pole goes to 30 degrees south and takes a 90-degree turn toward the sunrise. Okay, now this is just one point in time, and I'm going to stop the Earth on the equinox sunrise. They're going to rise at the same time, in the same spot. So if we drew a line on Google Earth, our lines, we have the same angle, and it's a great circle. It's a 90-degree turn, which makes it a great circle. So if we just kept going on the ground, we'd come around on our own ass. And but them lines are converging. If you draw it on Google Earth, them great circle routes toward the sun that's on the horizon are converging at about 6,000 miles off the coast before you hit Africa on the equator. To get 6,100 miles, they're converging. And my point would be, if you're going off the Polaris visual, if you pictured that in your head with the two different angles, you could see them lines never intersecting because they're different angles. So if I had laser beams coming out my eyes, they would hit Polaris, and they'd be the same distance apart as us on the ground because we're different degrees, different angles of each other. With the example of the sunrise.
All right, Brian, I'm going to stop you there. Brian, you're going to need to draw this. It's not working. It's quite confusing, and what I'd like to do though is instead to simply address the challenge. And then,
well, let me sum it up there real quick.
No, Brian, draw it out. I'd love to have you on another time, and especially if you can draw it out and we can actually have a more visual than this, because your word pictures aren't really doing justice to it, I think.
Well, I should have just led with this. The 30 degrees east, the 90-degree turns are great circles, and they're converging before they even leave the Earth. And if we left the Earth behind, and they're intersecting. Them great circles are intersecting, and if the lines were parallel, they wouldn't intersect. That's my point.
Yeah.
But, I do need to draw it. You're right. I need to draw it.
Draw a picture. All right. So here's your challenge, your submission. I do appreciate that you did have a submission, but you used globe everything in this. You used the one of the things in the
what globe did I use?
You use the measured radius of the Earth, of the globe Earth, 3959. Right, and that's based on the globe. So the point of the whole challenge is presuming that the Earth is flat, which means that any things that you'd use in it can't be based on the globe. Number one. Number two, what do you mean based on a globe? They're based on 1 degree curvature. I mean 1 degree. I wasn't finished. I wasn't finished. Then in the notes section of the, I think it's in the notes section of the challenge, it mentions that the particular light, the behavior of light needs to be something that's documented and seen empirically. So the upward bending of light that you need, this here isn't how light behaves. At least there's no known plausible mechanism for this. So I'll reject it based on those two things. If you disagree though, Brian, we can. It's up to you. If you don't agree with my decision, we can convene a panel of independent judges and take it out of my hands if you want.
I'll do this, man. I won't disagree, but I'll defend my my model and myself by saying this. I did a lot of work. I worked my tail off to come up, and I seem to be the first one that I know of to make the math even work or even close to working. And I did learn a lot doing it. Learned a lot about celestial navigation and all this shit. I didn't use a method that used radius. Like, at least I used empirical shit and came with some kind of argument.
You also didn't use a map. The map you used was a globe, right?
I don't expect $10,000, but I did come with I'm not going to argue on that because I seen the rules of the challenge, but I did come up with a method and an explanation and a site, something some people can go see to at least see some evidence of it happening, something feasible. And if you think that's worth something, McToon, I'll take it, but I don't expect,
when we meet, I'll buy you a beer as long as I don't have to drink one. How about that?
You're going to give the Globers $100 for giving this tournament.
You can do it too. You can use whatever method you want tomorrow at 6 p.m.
I use the method, man, and
it's different. It's a different measurement. It's different measurement, different stars. If your method works tomorrow, you could be the winner.
What do you mean if my method works? I just explained my method. We went over it.
Absolutely. So enter. I would love to see your entry. I think it would be fantastic. Even if you don't get the entry quickly enough, because I don't think it'll take long for an entry to be submitted. I would love to see your entry still. And I would
wait a minute. You based the my model not working because I couldn't, because I can't demonstrate light refracting like I modeled it out to. Yet I'll give you observations that you can't match on a globe. And then you say I'm using a radius of the Earth when I'm using a radius of Earth. We can never get to the middle of the Earth. We don't know. That's we can go 69 miles on top of the ground and watch the Polaris drop 1 degree. That's empirical. So you're kind of, to me, it's a little iffy, man.
I can know the radius. I can measure to get the radius of this particular sphere. Ignore that it's a globe. Just see it's a sphere. I can do that without drilling a hole and sticking the ruler into the center. I can do it through other methods.
Yeah, you can assume that
that's not an assumption. That's a measurement.
It's all assumptions, bro, because nobody knows what the heavenly bodies are or where.
No, listen. I'm specifically talking about one topic, measuring the radius of this exact one thing, no stars involved, of this particular sphere. I can measure the radius of this sphere without drilling a hole in it and sticking a ruler in through that hole. There's other methods.
I can really measure 1 degree change over 69 miles on the ground above the Earth.
And then one more thing then. You did use a globe map to get the positions as well, right?
That's what I would have accepted as a reason. Yeah. But that globe map it shows no elevation changes basically, and the changes and the distances are based. I'm basing them on my model, so that's the whole point. So just think about what I've said.
I'll give you this, Brian. I'll give you this. You did a lot of work, and I appreciate your hard work. I think it's a very fun and educational effort for you, especially, and for everybody else that's following along, just to see what you went through. So I appreciate that. How about that?
Yeah. I never knew you. I knew you weren't going to come off nothing anyway, dude. I gave you the coordinates. I gave you how I come up with them and gave you a legitimate model that no, I can't prove it 100%, no more than you can prove anything 100%, man. But I gave evidence. So I come with a lot, man. I come with a lot. But I'm not going to argue. It's your challenge, man. I never expected you to come off any of that money, not even for a second.
I tell you, if it met the requirements, I would not have an option. And if you said have people independently,
what map was I supposed to use, McToon? What map? I mean, if I'm basing
a map that's not this one, not this map. This is a globe. You can't use this map. You can't use this map for flat Earth.
I explained that it's empirical. The measurements are empirical, and
No,
why
What map? You asked what map should you use, and I can't answer what map you should use because I don't know. I don't know the flat Earth map. Every flat Earth map I've ever been presented, I tested and it failed. But I know for certain that you could not use this map because this map is a globe. And that's specifically.
So what map could I have used? So you wanted me to bring some kind of map. That's why I never entered this thing to begin with. And then until you changed your we could use here and use a map.
You cut out there. Say that again.
If I couldn't use a map that we use based on empirical values, I never would have joined when you changed your challenge.
I didn't change. Well, I didn't change it. I expanded it. There's two different challenges.
So what would I have had to have done? I would have had to have made a map instead of basing like known measurements and giving an explanation and a model of and making it work with light changing angles instead of the ground. I had to have a map to put it on, and what better than empirical Google Earth and explaining why we're getting the angle changes with a mathematical model.
Well, yeah, the problem with using a globe map is that because you're not trying to suggest that the Earth is a globe, you're trying to suggest the Earth is flat. So we got a kitty cat. This is, what do you think? This raccoon here.
All right, man, I'll drop it from there. I figured you'd give me a consolation, man. All that fucking work I did, man. But that's cool, man.
I'll buy you a beer as long as I don't have to drink it myself.
Whatever, man. I don't drink beer.
I don't either. All right, I got two more things here. William Foley says, please someone clip, I don't have the math for that.
So if there's any flat earthers out there watching, so we would have had to have made a map.
Of course.
And then plot it. I did make a map. You didn't make a map, okay? You took these charts. These charts are not globe charts, okay? The model is based on
what charts aren't
celestial sphere with the ground curving parallel with it. If you can call curved lines parallel, but to an extent I'll give you that. But like I said, I give it a method of how we could translate that and transform it to basically a flat ground with a flat plane. So that would make that map, it would unvoid the map. And so it's given an explanation of why the distances equate on a flat plane. I'll try and find a better way of putting my point to you.
Yeah, I mean, it sounds like you want to use this map.
No, I haven't tried that map yet, man. But that's azimuthal equidistant. When you're triangulating, you're basically triangulating the declinations. And
all right, so Brian, I want to be clear.
The only part you could claim use as a radius is the distance.
It's your arbitrary refraction ratio.
Is the distance, but that only comes in. That's coming in with an assumed radius, man. It's not proven that there's a radius. You're triangulating sideways.
It's been measured so many times. I did it myself 4 times. It's not assumed. It's measured. It's empirical. It's so completely measured so many times. But no. So you don't need to actually use a map. If you can do it without a map, you could. When you use site reduction tables, you don't use a map actually. It gives you latitude, longitude. You could output in raw latitude, longitude, right? Are you still there? Anyway.
Yeah, Google Earth is pretty much raw latitude, longitude, right?
No, it's not. Google Earth is a sphere. It is.
Well, tell me what map would be acceptable so I can go plot it and try it out.
I don't know. It's not me that's claiming that the Earth is flat. It's
Google
not
Earth is empirical distances, bro. So I'm using Google Earth and
it
showing you
is
how it works. It's flat.
Absolutely, but Google Earth
You're
is
telling me
a
I can't
sphere.
use the thing I just mathematically made work flat. Is what you're doing.
But it's not flat. Google Earth is not flat. Google Earth is a sphere. It's
Google
based
Earth
on a
is
globe.
a projection. Okay, it's a globe projection.
It is
Nothing
a globe.
more,
It's not a
nothing
projection.
less.
It is a globe.
It's a globe projection. Okay, it's not Google Earth.
I'm going to need a citation for that one.
What do you think? You don't think Google Earth is it'll tell you it's a globe projection. Okay, it's not proof of the globe.
I'm not saying that it's proof of the globe. I'm saying it is a globe map. And if you're going to use a globe map for a flat Earth celestial navigation challenge, you've just admitted that the Earth is a globe. Don't you see that?
Anyway,
Brian?
what I will do for you though is I'll put together I'll find these freaking sheets, but it doesn't matter. I'll redo them.
All right, let me read one more thing here from Truth.
What I'll do is I'll give all my examples and put them in a new video with my equations for anybody interested to see.
All right, and your channel name for people wondering is FE Tests, correct?
It's Flat Earth Test, capital F, capital E, capital T, Flat Earth Tests.
There you go. Okay, and then all right, so this one last thing here. Great circles toward the sun's GP are intersecting. Therefore, sun rays are not parallel. That's the gist of his argument, not understanding basic 3D despite hours of explanations and visualizations.
That's got to be paid NASA shill.
That was Truth Nerds.
Okay, he must listen to the conversation.
And Bob the Science Guy, here from Bob the Science Guy, at least he tried. So Brian, you are head and shoulders above all the other flat earthers. 100%. You did what none of them would try to do. So I totally appreciate that. And if I'm not certain that your motto would work or your method would work, but I would love to see it work on the challenge that's coming out tomorrow. Please do it, even if you think that you won't be in time for the prize. I would love to see you do it. I would absolutely love it, and I want to have some sort of a review, maybe on my website, a webpage, or maybe in a video of several different methods that people used.
Roger that. I'll put together a video also, man, a short video with some demonstrations, and then you after that, and then you can critique it.
Yeah, that'd be perfect. So, all right, Brian, anything you want to say before I move to the next video here?
Yeah, man, go to Flat Earth Test and check out the celestial equation. It'll show you, and it's a little bit modified. I enjoyed tonight, man. I didn't come accepting. I knew that I didn't qualify within all the rules and all that, but I did want to show you that, in my opinion, math isn't reality. Math doesn't prove things. Models and stuff are useful, but I don't think they're proof. I think it's a great debate, man. And like I said, I did enjoy it tonight, man, with Tune, and I will enter that, and I will try it out on a map too, just for the hell of it, to see what happens with that. And I'll send you that. You critique it, and maybe we'll talk about it next time, man.
All right. Awesome. Thanks, everybody. Thank you to everybody that sent super chats and messages and just joined in and enjoyed a fun conversation. Be sure to jump to this next one here, where we're going to find somebody and we're going to surprise them in a good way. So we'll see y'all later.